As I was saying before, last time we were talking about the statistical test we use for categorical variable. Categorical variable, just to remind you, are the variables that you say yes, no. Often you can change with the names, like dead, alive, male, female, and so on. Or they are at least less than 6, let us say, digits. For instance, mitral regurgitation is 0, 1, 2, 3, or in case you put 4, they are 5, so they are categorical, ordinal, not nominal. But anyway, now we are going for the continuous variables. And for these reasons, I changed a little bit the format of the lesson. So I will show you the problem, what we want to do. Later on, I will go directly in the statistical program to show you how it works. When I will start with the statistical program, I will tell you how in general it works in general. You will see that it is very easy. It is less difficult than you think. Okay. This is the last time we finished with this table. So you have how to compare categorical variables, nominal, ordinal. You have chi-square, the Fisher test, and in McNamara, Cochrane. These are different things. But before starting with the continuous variables, I want just to introduce you over a concept that you have to keep in mind. For instance, you are checking the hospital mortality in patient, elective, urgent versus emergency patient. And you know that the difference is statistically significant. Let us say this one. I will start to show you. Here you have statistics. You go for crosstabs, chi-square test, and this is the chi-square. Here you put one of the variables that you need. In hospital deaths, you want to check in hospital deaths versus emergency cases, means emergency, yes, no. Let us go somewhere here, there will be emergency. They are not, okay, emergency. And this is the result. I hope it will arrive soon. So the result, as you will see, but is evident, that is, this is a very significant. You see that you have 18 deaths globally, and there are in patients with emergency are here, 1. You have 18 patients with emergency and 3 deaths. And this is, and you have 2 deaths versus 95. So you have 5 deaths. These are the number of deaths. So this is statistically significant. And this is an important concept. However, this means that you know that it's statistical, but doesn't tell you the p-value by itself. What it means? You means that you know that there is a difference, but how big is the difference? So what we call the effect of the difference is what means that patients are dying in higher quantity if they are emergency. How much is the difference, which is the clinical meaning? And this is the concept of the effect size. I have to introduce you this concept because every time you are reading a paper, for anything you will find this, mostly this first one, odd ratio, OR, confidence interval, blah, 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 and a p-value. So you will have both. OR is the odd ratios, that is the ratio of the possibilities, and the relative risk that is more or less the same. And I want just to show, this is you see a list of the effect sizes, but we are not interested in the remaining that are in general more complicated. You see here the odd ratio and the relative risk that are the most important for not only categorical variable, but most of our studies. I want just to explain you what means and which is the difference between odd ratio and the relative risk. The odd ratio are used to quantify the risk that a certain population shows a certain disease. The procedure is different. If you have a retrospective study and you use the odd ratio, of a prospective study and you use the relative risk. Why there is this difference? Because when you are doing a prospective study, you choose the rules. and you are following your rules. In the retrospective study, patients are already there. So you must choose among the patients, not before the patient arrives, you choose the way you have to analyze the patient themselves. For instance, these are just, we want to study how many patients are diabetic in two populations of males. The first one with the coronary disease and the second one without the coronary disease. If your study is retrospective, we choose the two populations, with and without the coronary disease, and count how many diabetic patients are in both. So you decide the patient in the last year, the patient that are in the hospital in the emergency, the patient that are in medicine, depends, you decide which kind of patient you are choosing. Imagine that we have 100 patients in each group. In the group with coronary disease, 30 patients are diabetic, versus 10 in group that are no coronary disease. How can you compute the odd ratio? Believe me, it's the computer that is doing it. But just to understand what it works, you take how many diabetic you have in group A, you have 30 here. How many diabetic you have in group B? You have 10. The ratio is 3. Later on, you take the patient without diabetes. How many diabetics you have in the CAD group? 70. And how many you have in no CAD group? 90. Is 0.78. The other ratio is the ratio of the ratios. So 3 divided 0.78. That is 3.86. So the odd ratio describes the strength of an association of two data here that we can call binary here, CAD, yes, no, and the diabetes, yes, no. This association between two factors does not establish that one is depending on the other. It says only that they are associated. Later on, the clinical implications are up to you. The statistics does tell you if there is a relation. You can have perhaps that a patient with a coronary disease are taller than patient without coronary disease. What does means? Perhaps nothing. So the implication depends on you. Just this is the example we did. Here you have the chi-square, and here you have the odd ratio. You see here the odd ratio. This is 30 divided 10, 3.7, and this is the odd ratio. Is very significant, and both of them are very significant. I want to tell you one thing, that you can have the same odd ratio, but you have different p-values. This because there are two different concepts. I just did some example for you. And you see here, you have again the same, more or less the same. You see that the ratios are always the same. 3 here and 0.78 here. And the odd ratio is exactly the same in all of them. But you can see here that the chi-square value is totally different. Of course, it depends to you to understand what it means. Because let us say the first example. You have no difference between the two, let us say, mortalities. The first group is 6 and 14, means 6 out of 20 is, for instance, 30% mortality. The second group is 2 and 18. So 2 out of 20, there are 10% of mortality. I understand that there is no statistical significance. But on the other side, clinically, there are 3 times of patients that are dying in a group. So it depends. It's up to me to take to the clinical implication of what it means. But anyway, just to explain, there are totally different things. One say only statistics. What is the possibility to be different? That is the p-value. The other one tells you how big is this, the size, the effect of this difference. For the relative risk, if the study is prospective, we decide the criteria of the study and when it will start. We collect all patients with and without coronary artery disease and check if they are diabetics. The relative risk represents the ratio between the prevalence of the same event in two groups. For instance, again, 30 out of 100, 0.3, and 10 out of 100, 0.1. And the relative risk will be the ratio of these two ratios. Again, now is a 3 in favor of the coronary disease. This means that a male patient with a coronary disease is more likely by a factor of 3 to be diabetic if compared with a male patient without coronary artery disease. This is something that happens in the prospective study. For instance, here you just give you an example that we did. The relative risk is 3, and everything is really very significant. On the other side, I did exactly the same example that you find I gave you before. You see, you have 3 different relative risks, but they are totally the same in 3 different examples. But this t-square is different. Just again to show you that the relative risk or the odds ratio are a concept that is totally different from the p-value. But it's important because you need to know how big is the effect. If you are studying a procedure that gives you a better results or a lower morbidity or lower mortality, you must know how much is the impact on the clinical impact of this procedure. Now let us come to the continuous variables. The continuous variables are honestly the most diffused that we can use in our study. We have age, we have BMI. For us as a surgeon, we have ejection fraction, volumes, cross-clamping time, or anything you want. So now let us start from the beginning, comparing a continuous variable in 2 subgroups. For instance, you want to compare the cross-clamping time in patients who had ventricular surgery and coronary bypass with and without mitral valve surgery plus minus tricuspid surgery. It's evident that there is a difference. But anyway, let us quantify and to understand how to proceed. The procedure is always the same. Anything you want to compare, age or body surface, anything you want. The first step is to know if the variable that we are working on, that is the cross-clamping time, is normally or not normally distributed. If you remember before, we had 2 different possibilities for continuous variables. Normally distributed means to be more or less inside a Gauss curve, non-normally if they are outside a Gauss curve. I want just to show how to proceed. That is, here we have the variable that you are working is the cross-clamping time. Here there is we are evaluating the cross-clamping. Here is the cross-clamping. You see that the normal distribution is good, is higher than 0.05. So the variable is normally distributed. You can just to show you what you can obtain. For instance, you have here distribution histogram for the same variable, cross-clamp. You have, this is just what you can see. This is the distribution. You see that more or less the distribution is considered normal. So how do you compare it? You compare with let us say the most famous test is the t-test of student. And this is the test, independent sample t-test. You see, this program is very easy to use because here you have the variable. The first variable, again, is cross-clamp in both groups, of course. The filter means you must choose the 2 groups. We said the groups we have to choose are patients with the mitral surgery and tricuspid surgery in case. Here there is mitral valve surgery, no. Means there is no mitral valve surgery. And here mitral valve surgery, yes, 0, 1. In this case, you find directly the result. The result is the following. You have 89 in one group, 117 or 18 in the other group, 89 plus minus 30, and 118 plus minus 25. And this is statistically significant. So basically, you already reached your goal. You know that there is a difference, and you use this to do a table or to think what you are going for to the next step. The second step, you have to choose the right statistical test. We already did it. And the student t-test is the most diffused test that everybody, I think, knows somehow if you are working in the medical area, you heard about the t-test, or the student t-test. Another example. You want to know exactly the same, but evaluating a preoperative Euroscore in patient with and without left ventricular diastolic dysfunction. Again, you have to know if is normal or not normal distributed. You go here. Let me see if I can change this one. At least we can move more. Okay. Statistics. Again, summary statistics gives you the idea about the variable. Now you look, these are the list of all the variables that are in the database, and you put Euroscore 2, and you have a Euroscore 2. You see, reject normality. So the Euroscore in this patient is not normally distributed. What you do, perhaps you remember or not, you try to see if this can be used. In this case, you can use a parametric test. If you just to remind you which is the difference, a parametric test works with the real data. So if you have a 120 cross-clumping time or the Euroscore is 10, it uses 10. The non-parametric tests are working with the rank. Means they take, like the tennis, that is ATP is the most important, the easiest way. So the number one has 10,000 points. The number two can have 2,000 points or 1 point, but is the number two independently with the difference. So you understand that the non-parametric tests are not using all the data we have in our hands. So you try to see if you can use it. You see that now accept normality. So it means that after this trick, that is logarithm transformation, log transformation, you can use again the test we were using before. So the t-test for independent samples. Again, here you put the same, but we needed to change the variables. We are working with. Let me find where is the Euroscore 2. This is okay. Here is Euroscore 2. We change everything here. Euroscore 2 is here. And now we need to add the patient with, okay, this is left ventricular dysfunction. These are the groups that you are putting here. And this with this. Okay, and you find, this is the result, patient without ventricular dysfunction have a lower Euroscore than patient with diastolic dysfunction. 7.6 and 12.9 means here 13, let us say. This is the standard deviation. The p-value is statistically significant. So you arrived to this result. First you evaluate the, and you see here, it takes 20 seconds. You evaluate your variable, you put this in the statistical test, and it's done. You log transform in case it's not like here, and you do your job. Now let us take another variable. Why I just put this, because we need to do all the possibilities. Now we need to look at the preoperative ejection fraction in the same group of patients, with severe and without severe. Okay, let us go to the summary statistics, and here you put a preoperative ejection fraction. Okay, here pre-F. Again, you have not normality, reject normality. Again, you go in log transformation, reject normality. So there is no way. Ejection fraction is not normally distributed. So you cannot use a parametric test. You must use another test. And this test is the Mann-Whitney test. I will show you here. You go here, statistics. Again, rank sum test. Why? Because these are the non-parametric are using the ranking. And you see here, Mann-Whitney test. Okay. Here we have a pre-F somewhere. Okay. And we have here pre-F. You see here, you have the two groups, without and with left ventricular diastolic dysfunction and the prearrhythmic ejection fraction. At the end, you see here, you see that patients that have diastolic dysfunction have a lower ejection fraction than patients who have not diastolic dysfunction. And this difference is statistically significant. So this means that you have the possibility to go on with your process. For instance, in this paper specifically, I evaluated the importance of diastolic dysfunction in the outcome of this patient, and I found that this is really very important. But practically, using this database, you will, and this statistical program, everything will be very easy. Just 2 words before going on, 2 words on this program. You know there are a lot of statistical programs. SPSS perhaps is the most famous. You have STAT, you have a lot of them. Most of them are a little bit complicated. PSCC, the SPSS is a statistical package that needs to work on. So you need to spend time. What I'm using here, you see here, MedCalc. MedCalc, I was receiving advice by a friend of mine. It's very cheap and it's very easy to use. You need only to put all the, you see here, you have age. These are the variables you are putting: age, gender, Euroscore. You can put 0, 1 most of the time. You need the digits. Sometimes you can put male, female, yes, no. But every time you must use exactly the same word. Otherwise, the computer, honestly, the computer is very intelligent, but it's also stupid. It doesn't not able to. Is not flexible. And when you have this database, it will take more time for you. It takes 1 hour to build from an Excel sheet this database. When you have this database, the analysis is very fast. You can do everything you want in the time, as you see, we are doing together. And this, honestly, is very easy to be done. Let's go again to what we have to do. Now, another thing that most of us are using to see especially the result of surgery, we are comparing a continuous variable 2 times in the same group of patients. What means? For instance, we have the ejection fraction before and after surgery. You have let us say, the stroke volume or mitral regurgitation. No, mitral regurgitation is not a continuous variable. Some of variables, they can be evaluated 2 or 3 times after surgery to see if there is a benefit in what we are doing. You want to compare the end systolic volume index before and after surgery in the same group of patients. Again, you have to know if the variable is normally or not normally distributed. Okay, let's go back again to the same statistics. Summary statistics gives you the evaluation of only one variable. Let us find here. Okay, and the systolic volume index. Okay, reject normality. Log transformation. Accept normality. Good, so means that we can use another test. Which is the test we can use? The test we are using here, you have to use again the t-test, but pair the t-test. So this test is evaluating only the patient that have, when you indicated, for instance, before surgery and after surgery, and ignores all the other patients. Let us see here. The test, you have, before we had the independent sample, because we are using 2 different groups of patients. If you have the same group of patients, you are repeating the same evaluation in the same patient, pair the sample t-test. And here you need to put, I am looking for it, sorry, okay, this is the 1, 2, and here you are putting the filter. What was was in patient before and after surgery in the same group of patient. Okay. You see here you have a before, and now you have to do post somewhere. This is not, perhaps is follow-up, I don't know, there is. Okay, is this one. So you have before surgery and after surgery in the same group of patient. The computer, the statistical program knows because there is this name, a paired. Means that are only patients that have both evaluation. And you know that we have 108 patients, we have the same evaluation, and you have here the 76.8 and 50.5. These are the standard deviation, and this means that there is a statistically significant reduction or then the systolic volume index. And this is important, is the paired T-student. You have independent and the paired. The paired when you repeat the same evaluation into groups of patients. Okay. You want to compare the ejection fraction before and after surgery. Now, again, the variable, you know to know if the variable ejection fraction is distributed normally or not, but we know before, you remember we did the preoperative ejection fraction, it was not normally distributed. So for this reason, you must use another test. Again, let's go here. You remember, being a parametric test, this is a rank. Everything is ranking. And you see here, pair the sample. Basically the same that the student, the T-student, pair the T-student, pair the samples, Wilcoxon test. And here you put, I think, instead of this one, let us see if this makes it easier for us. Okay. Let us say what is ejection, okay, post F. So you have a before and after surgery, and here you see that the median was 26, now became 31, and this is statistically significant. So you are using a non-parametric test. Sorry for insisting on this, but it's important because if you are using a wrong test, you can have different results. And this is important to choose the test. You know, normally, not normally. Later on, independent if you are comparing two different groups, the same variable in two groups. Or is paired if are using two variables in the same group, repeated 2 times or more than 2 times, as you can see here. And this is, as I told you, this is the Wilcoxon test. Now, there is the ANOVA. Perhaps you know something about ANOVA. ANOVA is analysis of variance. Is another interesting test that is more or less the same, but gives us more possibilities. Basically, is like the t-test, but can be used in more subgroups. For instance, you want to know if there is any difference among the peak gradient in the follow-up in patients who had the TAVI using the SAPIEN or the core valve. Basically, you are comparing a continuous variable, that is the gradient, and the categorical variable, nominal or ordinal, can include 2 or more subgroups. I won't just, I will use this other one. Okay, now let us take the ANOVA, one-way analysis of variance. You have here the post-operative, you need to find here follow-up aortic stenosis, let us say this is the peak gradient. And the factor codes you can have here, okay, prosthesis type, Edwards or core valve. And you have the ANOVA that gives you here the mean, the number of patients, and you know that there is no difference between, is a 0.01 basically, and that means that there is no difference. It's evident that it is exactly the same you can use if you want a t-test. But the importance of the ANOVA is that you can use for more tests. I want just to show you for more subgroups. Again, in this patient, for instance, you want to use to evaluate the follow-up, let us say in another way, according to the outcome of the patient. So you have three groups of patients: outcome good, outcome the same, outcome worsened. So you want to know if the gradient in the follow-up has an influence on the outcome. And this is complicated because you cannot use a t-test because you have three subgroups. And this is a complication of things, but the ANOVA solves this one. So you have here outcome. You have the three means. These are the three means of the three groups. And you see here that there is no statistical difference. This is the 0.9. So you know that the influence of the gradient in three subgroups is not important, or there is no influence at all. So sometimes you have this necessity to do in three groups or in four subgroups to know if there is any difference between the groups according to the variable you wanted to study. You want to know if there is a difference in the creatinine clearance, for instance, depending on the outcome. More or less not the same, because the clearance of creatinine has to be evaluated now again. And you see that the creatinine clearance rejects normality. You try again with the logarithmic transformation. Now you discover the ANOVA, what you need, and reject normality. So you cannot use the same, but you can use, if you see here the ANOVA, there is the Kruskal-Wallis test. That is the same, but for non-parametric. Is again talking about ranking. Creatinine clearance, factor codes. Let us say what is the outcome. Okay. Again, you have here the median of the creatinine in the three groups, and you know that there is no difference between the groups. So again, if you have a parametric or non-parametric, you can use the ANOVA for anything is parametric, or this other test that uses the ranking. So remember, non-parametric and ranking. So everything is done by the computer. You cannot take one by one to make a picture to understand if they are normal or non-normal. The computer does everything. But this computer, if you see here, the summary statistics gives you the idea immediately, the idea of your variable. So you don't need to struggle for this. Later on, immediately you decide if you're going to the right or you are going to the left. Now, the same thing. You can repeat the different measurement in a way that you need in more subgroups, and you need to work on this. So basically, you can do the same. You have the same continuous variable under different conditions in the same subject, for instance, 3-4 times after surgery, and you need to understand what you want to do. Let us make just an example. Aortic peak gradient after TAVI, after discharge, sorry, here there is not a discharge, and the follow-up. You want to know if there is any difference, okay? You have not 2, but 3 measurement. Statistics, you take ANOVA, repeated the measures, analysis of variance. Okay, you take preoperative. No, this is not the good one. Peak. This is early discharge, and you have a follow-up peak. Okay, that is. So the result is that you see these are the bars that are indicating the gradient, 83 before, 18, 17. You see here that it works very well, and this tells you that there is an important statistical difference between the groups, less than 0.01. And this means that your situation, your activity is good, because there is a difference between the gradient, and every time you have a difference. And this is just here. This is the repeated measure. So, but you know, remember with the T-student you can do only twice. You cannot do 3 times. Here you can do 3, 4, 5 times, anything you want. You put this and gives you if globally there is a statistical difference. For instance, if you want to know, just to know how to work, you have 3 differences. The first, of course, is very high, is the preoperative gradient. You can use to know if the gradient is stable over time. You can compare only these 2. So the early discharge and the late to understand. So you can use the T-student. So you modulating your test. You are understanding where you are going to, what you are going to do, and to understand why they are doing this. The 2 factor is exactly the same, but you needed to do the same with the different, with not only 1 but 2 subgroups. For instance, 3 repeated measures according to the different type of prosthesis. See here, you insert here a group variable, and not a group variable here. Okay, this is the prosthesis. What do you tell? What does it tell you? It tells you this one. That there is a, sorry, okay. There is a difference between everything, but intergroup, no difference at all. And you can, let us say like this. No, this is not, doesn't work. I want just to show you what we can do. If box dots, let us see if we can do like this. No, it's not clear here. But you can have a picture from this anyway. And in the other computer, I think is more evident the program. So basically, you know that the different prostheses are giving you the same results, even with the 3 or more different evaluation. So we can conclude that there is no difference among the gradients, but the prostheses show the same pattern. And just to finish, I want just to, these are just a summary. Independent t-test, continuous versus nominal, distributed, non-normal distributed. Distributed, you have independent, ANOVA, the pair test for the same subgroup, one-way ANOVA, repeated measure, ANOVA single or 2-factor, Mann-Whitney, Kruskal, and Wilcoxon. So basically, I understand that this is a little bit categorical, but at the end of the story, you have 3 or 4 things to keep in your mind. That any variable, you must understand which kind of variable we are talking about. If it's parametric, is normally or non-normally distributed. If it's normally distributed, you can use the mean plus the standard deviation, otherwise the median. If you are anything you are comparing with the normal distributed is easier and is more efficient. And most of the time you can use the T-student. The T-student for either independent or paired. If it's not normally distributed, you can use here the Mann-Whitney, Kruskal, and Wilcoxon, and you use for all of them. Of course, the power or the importance of this test is less, so you need more difference to be evident rather than the other one. But this is really very important. As I can show, I show you this program. This program, honestly, is very easy to use. You need only an Excel sheet where you put all the data. Later on, you copy the Excel sheet column by column and put it here in the program, and you are ready to work. And when you have statistics here, you see this later on, of course, next lesson there will be the last one on the statistics, of course. We can check the survival analysis. They can do everything. So you need only to click and to put the right variable. So what is the work you have to do is not the analysis. The analysis is the easiest way to do. The work is to prepare a good database. When you are preparing a good database, everything is very easy. I can receive today a database that is well done. I can tell you that in a few hours, the time to change from the Excel sheet to here and to analyze it, in a few hours, I know which is what I can do with this database. If I can write a paper, I cannot make a presentation or not, because the data are there. So we need to be very precise in the database, and later on, strangely, the statistical things, the statistical tests that seems very difficult are the easiest thing to do, because you need only to know 3, 4, 5 things. When you know this one, how to use the categorical and the continuous variables, you know everything. Of course, there are 5% of medical statistics that is very complicated, and you need someone that is a really specialist. But remember that most of the common medical statistics can be done by you with a computer and without help of anybody. And this is the most important thing of these programs. And it's not because I like this program instead of another one, but I found it so easy and also easy to use by me that I am not an expert. That is really, it changed my life. And I think that the message is that the program is always there. What is important is the database. So having good data give you a good analysis. And the analysis, honestly, is the easiest things to do. So the importance of collecting correctly data is the key message of all the lessons of statistics. Because if you put a garbage in the system, you will have a garbage. You cannot have good things from there. Thank you. Okay.